Good afternoon, dear committee and the guest. My name is Armen Hovhannisyan and my supervisor is Levon Hovhannisyan. And now I'm going to present my capstone project on the topic Human Motion Energy Harvesting System for Charging Prosthetic Devices. So let me have a small introduction. Let's understand why this research is important. As the time goes forward and the technologies grow and the civilization develops. However, the development doesn't allow us to solve all the conflicts in a peaceful way, and the technologies still doesn't allow us to predict all the disasters. So wars and disasters happen, and because of these, many people have disabilities, and the need for usable, functional, and portable prosthesis rises. And so let's see what we know and what we don't know. We know that theory claims that harvesting energy from human motion offers a promising, eco-friendly, and sustainable power source. And we know that there are several examples of human motion energy harvesting system that work fully autonomously. For example, the hand watches, that automatic hand watches, or that collect energy from hand swinging, or collect energy from human body motion, human body temperature. Also, there are, for example, electronic cars which collect energy from recursive systems. And for the question arises why we don't have that kind of system for prosthesis, and to answer that question, the experiment was implemented. So the idea of the experiment is to explore based on the real users' opinion and their ideas, use real users' opinion and ideas to understand how and where the prosthesis parts can be applied, put it harvesting techniques, and how it can work together, and will it be. And the hypothesis of the exploration is that by using hybrid energy harvesting systems, we would be able to collect enough energy for our daily usage of the prosthesis. So what is energy harvesting? Energy harvesting is a conversion of ambient energy in the environment into electrical energy for use in autonomous electronic devices or circuits. However, all kind of harvesting techniques cannot be considered for us because we are concentrated only for the techniques that can be used to harvest energy from body motion. And as you can see from body motion, there are two types of energy, biological and mechanical, that can be harvested. So let's see what are the most popular harvesting techniques and understand their working principles. So here are the 6 most popular ones. The first one is piezoelectric harvesting, which converts mechanical stress into electrical energy using piezoelectric materials. The electromagnetic induction, it works based on Faraday's law, which says that when the magnet passes through the coil, it makes the current flow from each side to another. Triboelectric nanogenerators is the generators that we all know from the school, that when the two materials we touch or separate, they are exchange charges. Electrostatic energy harvesting converts mechanical vibrations into electrical by varying the capacitance of a system. Thermoelectric generators use the heat produced by the body, and kinetic energy use the bendings, movement, and mainly used on the converting. Mainly are used with mechanical linkings. So to understand which of these techniques can be applied to our research, let's understand our requirements. And our requirement is that all the harvesting system should be embedded in the prosthesis, and the user don't need to wear any additional different material clothes, have belts, wears additional special shoes, and care wires. And also, furthermore, the resulting device should ideally not increase the metabolic cost, which means that it doesn't force people to do any additional actions during his daily life besides of his usual ones. This is the prosthesis which was the mainly explored during this exploration. This is the Osur eye limb prosthesis. This was chosen because this one is one of the most popular one in Armenia, and majority of 44 Artsakh war participants use those. So here is the image of the prosthesis, and it has three main parts that we can use for our harvesting system housings. The first part is stump receiver. The second part is plastic arm, and the third part is the palm or eye limb itself. So let's go one by one and understand how each part can be used for energy harvesting. So this one is the stump receiver. As you can see in these holes, there should be the sensors, and the sensors capture the triggers from the muscles to open and close the hand. And here is the diagram of the piezo plate, which is chosen based on the sizes of. For this example, I do all the measurement for my prosthesis. That will be suitable and can be placed inside this stump receiver. The stump receiver is the best place for placing piezoelectric plates because, as I mentioned, there are the sensors that capture the muscle force, and the piezoelectric materials need stress. So every time the user will stress the sensors to open or close the palm, the piezoelectric plates will also be stressed, and also besides because of elbow movements from up, down, and left, right, and also stress will be applied to this plate. Besides, it is environmentally stable, so when the user will sweat or the temperature will be higher because of always connecting with human body, the effect of the harvester will not loosen. So the second part is the plastic arm, which is mainly have the aesthetic is the design, so it connects the stump receiver and the palm, and this is the view from the top. So I put this image so we can see that there is it's nearly empty. There should be just the wires from the sensors to the palm and the small battery that the prosthesis uses. And here is the prototype of energy harvesting, which is the electromagnetic induction energy harvesters, which is a small tube which with coils around it, and a small magnet is put inside, and all this mechanism is placed horizontally inside the plastic arm, and so when the user swings his hands, the magnet goes left and right and collects and make the current flow. So because of its small sizes, the amount of energy harvester can be varying depending on the stump size of the user. Also, this is beneficial to place exactly in this part because there are no such a electrical system that the existence of magnet will disturb working. All the boards are inside the palm. And the third was suggested harvesting system is triboelectric energy harvesting. So the manufacturer claims that the prosthesis should always be worn with a glove, which is made from the silicone and rubber. And as a silicone rubber is one of the good one and best explored materials to use in triboelectric energy harvesting. It is triboelectrically negative. So by pairing with another material which will be positive and placing it accurately in the joints of the prosthesis, we can harvest energy. So in our case, we have two joints on each finger, and not considering the thumb because its movement is very different. So by putting harvesters, small materials which I choose to be nylon, that is the one triboelectric couple that works better. So by putting small parts here, and also in the other side of the prosthesis, we can have 56 centimeter square area for our triboelectric energy harvester. So let me a little introduce how I calculated the results. So firstly, to evaluate my result, I calculated the energy requirement, and I used the datasheet of the BioLimp and average usage of the prosthesis. So in the datasheet that was mentioned, the number of cycles that the prosthesis should make with a full charge battery. I calculated the energy required for one cycle, and by multiplying with average, I found the energy requirement for a day. For piezoelectric materials, I'll take the datasheet information, calculated the permittivity of the piezoelectric plate. With the help of force meter, calculated the average stress applied on the sensors, and calculated the daily energy produced for two plates, because there are two sensors, so two plates will be more comfortable and will generate more energy. The first electromagnetic induction was calculated based on the prototype I've created. So because of creation, I know how many number. Քանակ պտույտների էլի հասկացա, քանիսներ. And by taking the average number of hand movement during the day for a single, I have calculated the energy harvested for a single module. And lastly, the triboelectric energy harvesting, calculated based on the theoretical values, because the prosthesis is under the warranty, and touching the palm may cause some issues. So that's why we decided to keep away from it. And all the measures and calculations in this part was done theoretically. And here you can see the theoretically founded results. And as you can see, the energy requirement is much more higher than the energy that can be harvested, even in the idealized conditions. And this is only the values that we receive from the harvester. So taking into account that they need to pass through the circuit, and will somehow they die out. So the result is not as good as expected. So what are the risks we have having this kind of result? This actually, obviously, the system will not generate sufficient power to meet daily energy demands. Increased design iteration time and inefficient energy conversion is another risk, because to embed and implement all the system will take time, will rise the cost of the prosthesis and the design iteration time. However, the result will not be satisfying. Adding additional components to the prosthesis will add its weight and make it uncomfortable, because of which the system may be refused. Actually, even now, when no additional systems are added, many users who have the prosthesis done does not wear them. And last but also important one, all of the system is very expensive compared to the one or several batteries that now is put it inside the prosthesis and can serve for 5 days. So to sum up, through modeling, analyzing, and calculating energy output, it was determined that even under optimal conditions, the cumulative energy gathered from typical daily prosthesis use is significantly lower than energy required to sustain battery operation. Thank you for attention.
I think very important area of research, especially given that in our society it is a hot topic, and even that the conclusion was not sufficient to warrant development of such devices. Very, very impressive research. Very impressive.
Thank you so much.
Am I correct in reading the numbers that the amount of energy produced was 1,000 times smaller than
Yes.
what is required to run the arm?
Yes, you're correct.
Roughly.
Very, very small. Actually, it was surprising. I thought the piezoelectric material would be the highest one, but how many times I checked, I found these values.
And there's nothing that can be done to improve. I mean, 1,000 is a very large.
To be honest, I've explored the solar panels also, and I even ordered some parts and make experiments. However, lately I saw that the solar panels are not considered as harvesters from human body motion, but they are still sustainable and green way to harvest energy, so it can be applied, but it's not inside the topic of this exploration.
You know that there are some watches that wind themselves when you move your hand?
Yes, actually, it was one of my motivations. So I imagined that we have an example working, and we have a device with much more higher spacing in it, so we can use it.
What if they'll just like humans walk, or do exercise, or do some actions that might be
Meaning using other parts of the body to
they're
run
nearby,
this.
My question.
but
was
they're
to make the device independent of body, no additional wiring, etc.
sure. But if you're like many orders of magnitude off, maybe you start to look nearby, but not too far away. I'm just wondering, did you consider the sort of like everyday, or maybe I don't know, I don't have enough experience in this, but maybe in like physical therapy, exercising, or other related activities which are going to be likely for let's say a upper extremity prosthetic user. I just wonder if there might be some very nearby energy sources, to use a broad term, that might be worth looking into.
They are, for example, the walking that you mentioned is a very good source of energy harvesting. However, the users of this prosthesis, as much as I've contacted with them in the rehabilitation centers, they are very sensitive. They are not interested in additional movements, to be engagement in the sport, even when they are, for example, doctors say that they should do some experiments, and even it's free if for example, kinesist comes and works with them, they refuse many times. So it will be hard to force them to wear, for example, special shoes to walk some for spatial distance to harvest energy for them.
So that's all. You're entering the very much more difficult world of patient care and psychology and others. I think within the scope of an engineering thesis, it might be worth, especially as we're putting comparative, what's the potential of some of this, and then you get into behavioral change and adoption ratios and things like this. I'm just mentioning because if at the end of the day, and not that the capstone needs to result in commercialized product. But if you find yourself that many orders of magnitude off from what might be a realistic future implementation, it might be worth even posing some thoughtful future work directions that might be more realistic, something like that.
Okay.
Have you had a chance to, for advisory for some expertise outside of Armenia who has their hands on these topics or problems? How is your study research of how far it went? What are the similar experiences outside of Armenia? And moving forward with this, what would you like to do from experience exchange and getting more knowledge from worldwide expertise?
To be honest, as much as I explored, I have met many different harvesting systems, but exactly the one that the engineers would like to embed in the prosthesis system, I wouldn't meet that yet. There were different ideas of using gloves, which from where I take the ideas for my case, because I also should always be in the glove. But for this complex solution, for different harvesting techniques and combining them, I haven't found explorations, to be honest. I have some talks with my prosthesis service who give me the service of the prosthesis, contact them. However, they also didn't give any useful feedback. Yes.
Yes, there is an experimental process of attaching the robotic arm to human, and with time, they will be able to connect the nerves into the wiring, into the system. In fact, I was talking to Aram just a few days ago that we have similar product that we are trying to maybe bring it to university and make it built in Armenia. So there is possibility even building a fingers that will be acting according either by videos or but to adapt it to the human will take a long process and it takes a while till the body accepts the arm and start acting. So there is an experiment in that field.
Yes, actually, I'm familiar with that experiment. That I guess it was in the Stanford University, and it was just a prototype, and now it's not in the production. But it was saying that there are 5 sensors that can be attached, and the human will have reverse feeling also.
We work with the university in Texas in similar.
Again, we like collaborations. Thank you.
Thank you.